All right, hello again, folks. We are going to start chapter 3 today with section 3.1, which deals with symmetry. The entire chapter 3 is going to lead us through some things with functions. We're going to look at graphs. We're going to look at some functional notation, things of that sort. So we're going to start with symmetry and specifically dealing with symmetry of functions. All right, so let's not waste any time. Let's get over to our notebook. And when we talk about symmetry, the first type of symmetry we're going to talk about is point symmetry. Now, with point symmetry, what I'm talking about is something that has symmetry in the idea it's a rotational symmetry. All right. First, I want you to kind of connect that word with it. It's rotational, meaning if we have a point and I have some shape that goes through that point, which I missed entirely. If I have a shape that goes through that point, say like this and like this, what it tells me is if I rotate about this point, if we say this has point symmetry, if I rotate about this point, and this shape is an example of it, if I rotate it around here, I would get back that original shape with less than a full turn. Now, obviously, if I rotate any shape around a full turn, I'm going to get back that shape. But less than a full turn, and I get back the shape, I have rotational symmetry. All right. Now, in terms of functions, the type of point symmetry that we're interested in is symmetry with respect to the origin. All right, our point that we're talking about with point symmetry is the origin. All right, that's our point, that point 0, 0. All right, so we're going to look at functions that have symmetry with respect to the origin. That's going to be key for us, is we want to know what kind of function does that. All right, now how do we figure that out? Well, let's talk about what it is first. If we talk about with respect to the origin, I want to give you generally some key exemplars all the time, something that demonstrates what that would look like. And let's do this first. Let me get a graph here kind of quickly. And if I do this, and that should give me enough. All right, we'll do that. Okay, so when we talk about symmetry with respect to the origin, what I'm talking about is, for example, y equals x cubed. Y equals x cubed, we know goes through the origin and through the point 1, 1, and then jumps up to 2, 8 and 327 and so on. And does the same thing in this direction, goes out -1, down 1, and goes down to -2, -8. So this graph is an example, one of the most basic examples of origin symmetry. If I rotate this, I would get back the same shape with less than one full rotation. So it has point symmetry, that point being the origin that I'm rotating about. So this is a graph whose symmetry is with respect to the origin. Now, there are some definitions. Whoa, I did not want to do that. Let me do this again. Move that back where it needs to be. All right. Now, again, when we talk about in terms of definitions, what is symmetry with respect to the origin? Your book will tell you these type of, I think, I don't want to call them confusing, but I think they're less accessible to most people. If I talk about f of -x being equal to -f of x, for example, that is a book definition of symmetry with respect to the origin. When we talk about a function, if we take f of the opposite of x, it should equal the opposite of f of x. Now, sometimes that's hard for our brains to wrap itself around. I like to use a more basic way of approaching this, because what we're going to be asking you is we're going to give you a function in functional notation and ask, is this function or does it have symmetry with respect to the origin? And what I would use as a test is this definition. If AB is on the graph, then it has to have also, I didn't leave myself room, -a, -b. All right, if AB is on the graph, then we know that -a, -b also has to be on the graph in order for it to have symmetry with respect to the origin or origin symmetry. So what does that look like? Well, if we think of our point here that we talked about, we have this point 1, 1. That's our A and B. Well, if you think of what it means to be -a, -b, it would be -1, -1. That point is also on the graph, and that works for any point on this graph. I don't know why I wrote 2 there. -1, -1 would also be on this graph. So for any point we find on this graph, 2, 8, -2, -8 would also be on this graph. So for any AB, there must exist a -A, -B on that graph in order for it to be symmetric with respect to the origin. Another way of describing a function that is symmetric with respect to the origin is to call it an odd function. Now, why do we call it odd? It's just one of those things that you're going to see. I think it has something to do with the fact that this happens often with odd exponent functions or odd degree functions. So when we talk about odd function, it kind of matches with y equals x cubed. So if you want to make that connection, it might help you remember that's an odd function. An odd, if they tell you, is this an, or ask you, is this an odd function? You want to look and see. One easy way to see it is if every exponent, every variable exponent in that function is odd, then this is an odd function. All right. If every exponent is even, it's going to be called an even function. We're going to get to that later. If it's a mixture of even and odd function or even and odd exponents, then it's neither. All right. It's only those special ones that are odd functions. All right. And again, we'll go back into how we use this momentarily. First thing, I just did that again. First thing I want to do is get into other types of symmetry. We already talked, this is the point symmetry, as we said in the beginning, which is a rotational symmetry. Specifically, we're going to deal with symmetry with respect to the origin. That's our only point symmetry. All right, so now, line symmetry. Line symmetry is their other type of symmetry. We've got 4 of these. And this is that, when we talk about line symmetry, we're talking about folding symmetry. You've done this in, when you did it in geometry, you had a piece of paper, you created a fold in it, so you had this folded line of symmetry, and you had maybe a point on this side that you were asked to reflect. And you reflected it by folding that paper, and it would lay on over here, and you could draw that. Or you had a shape that once you had it on this side, you could fold this paper, and it would lay on the other side, and that would be this line of symmetry that they were with respect to. All right, that's the type of symmetry we're talking about, is that folding symmetry. And we've got a few of those. All right. The first one I want to deal with is y-axis symmetry. I want to deal with y-axis symmetry because, again, it has a very basic sort of exemplar, and that's y equals x squared. When we see a y equals x squared graph, we have a graph that does this, right? We know it has this parabolic shape. Y equals x squared has y-axis symmetry, saying it means that this y-axis is our line of symmetry, meaning any shape, any point on this side is reflected to this side and is still on the graph. All right, so what does that mean in terms of our A and B's? If I have A, B on this side, well, what do I have to have? If this is a distance A and this is a distance B, then over here I would have a distance -A still at a height B. So this, the way of defining this one, so to speak, is saying that if AB is on the graph, then there has to exist also -AB on that graph. All right, so you have to have the opposite of x would give you that same y as x gave you that y. All right, now the reason I bring this one up first is because this is also described as an even function. Why do you think it is called even? Well, for much the same reason. We've got an even exponent. And if you ever have a polynomial with all even exponents, then it is going to have y-axis symmetry. It is going to be called an even function. If it has mixed, again, it's neither even nor odd. If it has all odd exponents in that polynomial, then a polynomial in one variable, I should mention that, then it would be a odd function if it has all odd variables. All right, so again, even and odd right off the bat. Odd is an origin symmetry, y-axis symmetry is even. All right, so that's one of our line symmetries. We got 4 of these. All right, our next one, if we have y-axis symmetry, we can also have x-axis symmetry. So x-axis symmetry, what does this look like? Well, I'm going to try drawing a little bit neater axes this time. I don't like those other ones I was drawing freehand. So x-axis symmetry. When we have this, what we're talking about is symmetry that, our line of symmetry, I should say, falls along the x-axis. All right. So now we're talking about graphs that have a shape that would be reflected across the x-axis, like maybe something like this. This is y equals the absolute, or the square root, plus or minus square root of x. All right. If we did something like this, we have x-axis symmetry. Now, again, if we want to talk about how do we define x-axis symmetry, there's no special name for x-axis symmetry, by the way. There's no even or odd or anything like that. This is just x-axis symmetry. It is a line symmetry. And if we take this point A and B, again, out A, up B, well, what else is on there? Out A, down B. So for each point A, B on this graph, or any graph that has x-axis symmetry or is an even function, I'm sorry, it's not an even function, is x-axis symmetry. If AB is on the graph, then there exists also on that graph a negative B. All right. So again, just separating these, we have y-axis symmetry is our even symmetry. Looks like this. If AB is on the graph, negative A, B is on that graph. For x-axis symmetry, AB on the graph means A negative B also has to be on the graph. And I did not label that down here. This would still be A out, and it would be negative B down. All right. So those are our first two line symmetries. Let's go to a new page, and let's do our last two. The next one, the line y equals x. What does the line y equals x look like? Well, hopefully you're familiar with that by now. We've used it a couple times this year. Oh, that is not where I wanted it. There we go. All right, now if I do this, all right, so y equals x. The line y equals x. I want to do this. Through the origin, and would look like that. All right, that would be, whoa, I don't want that. I want this. All right, so this is our line of symmetry. Now, what could we use to look at a graph that has y equals x symmetry? Well, the most common is, and we've dealt with this one, y equals 1 over x. That's our hyperbola. It does this. And this, right? Y equals 1 over x. Now, that means when I reflect across here, when I take a point, and let's do this in color. If I have a point here, it should reflect across to here. And in fact, it will on y equals 1 over x. Now, think about what that means. If I had, say, this was at 4, I would have 1/4, right? So this would be at 4, 1/4, right? Because 1 over x. If x was 4, y would be 1 over 4. Now, on the other hand, if I look over here, if I say, how would I know the reflection, I guess, is the way I'm looking at this. Well, what you'll find is over here, if you have this reflected across, you would have the point 1/4. And if I put 1/4, 1 over 1/4 is, in fact, 4. And so what happens here? If I have, for y equals x symmetry, if I have symmetry with respect to this line, if AB is on this graph, then what else has to be on this graph? Well, what did we do? We switched x and y. So if AB is on the graph, then BA has to be on the graph. And that's how we define the y equals x symmetry. That reflection from this side over to flipped or reflected across this line to this side. Okay, same thing would happen down here. All right, so that's y equals x symmetry. Last line symmetry you have is y equals negative x. And y equals negative x, again, has a similar appearance. It is on an axis going instead through the origin with a slope of -1 instead of 1. And it's going to have the same idea. Now, I could use y equals 1 over x again. Because if we look at y equals 1 over x, we know it does this. I drew it a little bit closer this time. And this. And what do we know? We know if I take a point on this graph and I reflect it across this line, it would show up on this part of the graph, this piece of it. Okay, so how do we define this? Well, think again. Let's just think of a point. If we have 1, 1 on this graph, what would this point be reflected across? This would be -1, -1. Now, that can be a little disconcerting. As you look at this, well, then we just take negative x, negative y. Let's go out a little bit further, and let's go to 2. If we go to 2, and I put 1 over 2, I get 1/2. So if I want to go over here, if I just took the opposite of each of those, I'd go what? I would take -2 and -1/2. Yes? So if I do that, I'd be going over negative, this was -1, I'd be going over -2 and -1/2. Is this point, now that looks like, okay, that works. But is that this reflected point? No. In fact, what you're going to find is this is the reflected point for up here, where we're at 1/2, 2. The reflected point for 2, 1/2, remember, we got to reflect straight across this line. So when we reflect straight across this line, if we were to fold this point, 2, 1/2 would show up here, which is in fact -1/2, -2. So what happens? These switch and we take the opposite. So now, if AB is on the graph, what else has to be on that graph? Well, -B, -A. We switch them and take the opposites. Everything changes. All right, that's how that reflection works. So these are our symmetries. This is just the basics. What I want to do is look at some problems. I want you to see how do we use this. And let's look at an example. They're going to ask you to determine whether something has, let's see, determine if f of x equals -12 over x has origin symmetry. Well, how could I tell if that's true? How could I tell if that has origin symmetry? I could graph it. If you graph it on your calculator, what do you find? If you graph this on your calculator and I put 1 in here, right? If I put x equal to 1, I'd be at -12, so I'm down here. And as I go out, this is going to come in closer and closer and do this kind of thing, right? And it's going to do the same thing on this side. Again, you can graph this on your calculator. It's one of the quickest ways to do it. So, well, that side, it should be a little bit deeper, just like the other one. All right, so how do we know if this has origin symmetry? If I can reflect across. And what else do we know about origin symmetry? Origin symmetry means if AB is on the graph, then that implies that -A, -B is on the graph, right? So let's look at that. Let's pick a point. We just said we know that if x equals 1, we would have -12. So what does it mean? If I want that, then if I put -1 in, I should get -12. For this to be true, this would have to be true, wouldn't it? I'm sorry. We'd have to get -1, 12. I got carried away. We got to take the opposite of each of these. So if I put -1 in, do I get, when I plug it into this function, do I get +12? Absolutely. And you could pick other points. If you want to be sure, you could pick another point. We could go back here and say, all right, if I put 2 in here, I would get -6, right? I'm just plugging it in here. X is 2, -12 over 2 is -6. So I should be able to take the opposite of my x, so -2, and I should get the opposite of my y, which is 6. If I plug -2 in here, do I get 6? Yes. And you can do this again and again, but what you're going to find is yes. And you can look also at your table of values. I should mention that. Table of values helps you with this a lot on your graphing calculator if you graph this, right? You can look at that. So does this have origin symmetry? Yes, it does. It passes the test, so to speak. Let's do another one. If I gave you f of x equals x to the 5th minus 2. Again, if you graph this on your graphing calculator, you're going to find it does something like this and like that, right? So if it has origin symmetry, I should be able to reflect it about this. Now, for those of you who were listening before, if it has origin symmetry, we call it an odd function. We said if we have a polynomial, we'd have to have all odd exponents. We do have an odd exponent here, but this is really 2x to the 0 power, right? X to the 0 power is just 1. But at 0, we consider an even power. So this is the case where we'd have 5, which is odd, and a 0, which is considered even, or least. All right. So this would not be an odd function. This does not have that rotational symmetry. And you can test points on it too. If you were to take something simple like plug in x equal to, oh, I don't really need that parenthesis. If I said x equals 1, then y would equal -1, right? Because 1 to the 5th is 1, and -2 would be -1. Now, if that, again, if it were to hold, I should be able to take the opposite. X equals -1. If I plug in here, I get -1 minus 2. Y gives me -3. That does not follow this pattern, right? Does not give me the opposite of each of these. The opposite X does not give me the opposite Y. So this does not pass that test either. All right, because that's got to work for every point on the graph. So this would not have origin symmetry. All right, let's do some more tests. Let's see if these have any symmetries, are point or line symmetries. All right, let's determine any symmetries. All right, so let's see what we got. X plus Y equals 6. Would that have symmetry? Well, this is the graph of Y equals -x plus 6, right? And so we're going to go up to 6, and we'd have a slope of -1 coming through here. So it would go through 6 this way. Right? And we would have this graph. So let's look at this. If we talk about origin symmetry, if I have any A, B, so for example, I know 5, 1 is on this graph, right? Let's use that as an example. 5, 1 is on this graph. Is -5, -1? No. All right, so let's look at x-axis symmetry. If 5, 1 is on this graph, then 5, -1 should be on this graph. It is not. That'd be down here, right? X-axis symmetry, this is our x-axis. Y-axis symmetry, if 5, 1 is on this graph, -5, 1 should be on this graph, right? It isn't. So far, we've already discounted that it can't be origin symmetry because -5, -1 is not on this graph, right? Whoops, I put the parenthesis in the wrong spot there. So -5, -1 is not on this graph. So it's not origin symmetry. No to origin. This one, 5, -1 is not on this graph. So we can say it doesn't have x-axis symmetry. No. Y-axis symmetry would mean -5, +1 would be on here. That's a no. So no y-axis symmetry. What about y equals x? If 5, 1 is on this graph, again, y equals x would go through this point. So if 5, 1 is on this graph, 1, 5 would be on this graph. Is that true? That is, isn't it? If you think about this, and I use 5, 1, x is 5, y is 1. If I talk about y equals x symmetry, then we said if 5, 1 is on this graph, then 1, 5 has to be on this graph. It is. 1, 5 makes this true. So let's try a -1. If we go to 7, -1, right? 7, and I'm just grabbing points. 7, -1 is -1, 7 on this graph. Absolutely. So does this have y equals x symmetry? What do you think? I would say yes. It has y equals x symmetry. Now, what about y equals -x? Y equals -x goes this way. So for 5, 1 on this graph, we would have to have -1, -5. -1, -5 is all the way down here, right? Is that there? No. So the only one we have is this one. You get the idea how you can test these? All right, let's do another one. If we want to find out any symmetries that, let's say, x times y equals 3. Well, I want to think of this as y equals 3 over x. Y equals 3 over x, we know, is like this, right? Because that's our 1 over x graph times 3. So we could say we know that there's a point that would be at x equals 3, we would be at 1, right? So 3, 1 is on this graph. Now, let's go through our symmetries. Origin symmetry. If 3, 1 is on this graph, then -3, -1 has to be on this graph. Would -3, -1 be on this graph? Absolutely. If I plug in -3 in here, it would give me y equals -1. So origin symmetry, yes. What about y-axis symmetry? So this is an odd function. Y-axis symmetry says that if it's here, 3, 1, it also has to be over here at -3, 1. Y-axis is no. X-axis? X-axis, if 3, 1 is on it, then 3, -1 has to be on it down here. That's a no as well. Y equals x. Y equals x says that if 3, 1 is on this, then again, this is y equals x is this way, right? Then 1, 3 has to be on it. It has to reflect here. Is 1, 3 on here? Yeah, if I put 1 in for x, it would give me 3, wouldn't it? So y equals x is a yes. What about y equals -x? Y equals -x would say -1, -3 has to be on here, right? -1, -3 would have to be on here. That looks like it would work. -1 in here would give me -3. I say yes. So this has origin symmetry, y equals x symmetry, and y equals -x. So that's what we're going to be asking you to do. Now, they may ask you some other things too. They may ask you a question like this. They may say, is f of x equal to absolute value of x an even function, an odd function, or neither? Well, think about that. If we talk about y equals absolute value of x, and this is a bad drawing of it, we have this. What kind of symmetry does this have? In order for it to be an even function, it would have to have y-axis symmetry. It looks like it does. Odd function, it would have to have rotational symmetry, meaning I could rotate this around and I would get the same point. In other words, if 1, 1 is on this graph, which it is, then -1, -1 has to be on this graph. It is not. So this is an even function. All right. We're going to get more work on this. It takes a little bit of getting used to. Use your graphing calculator to visualize these, and use your table of values to help you find quick values to use as x's and y's. And you'll find this goes a lot faster. All right. You can use your y equals second calc button also as a tool for this. There's quite a few different ways you can go about it. So that is a rather long lesson to start the new chapter, but it's one that we're going to work on for a little bit. So you really need to understand these symmetries. Have a wonderful day, get the homework done, and I will see you tomorrow to answer any questions. Have a great day.